right, we are looking at verifying trig identities, and this is a pretty big skill for us. The purpose is to manipulate these trig expressions so they're easier to solve when we view them as equations. So we'll be looking at equations next time, and the trig functions outputs, if you remember, the trig function outputs are ratios. So they're ratios of sides. And because they're ratios, some of them repeat, and there are only so many combinations. So a lot of them have just surfaced as identities. So we have these identities in this chart, and I'm going to fill out these reciprocal identities and quotient identities, and you might already know them already, so we'll chat about them here as I fill them out. Alright, so there we have the reciprocal identities filled in and the quotient identities filled in. It's important that we're flexible in knowing that sine's reciprocal is cosecant, and that we can rewrite sine as 1 over cosecant theta, and then as such for the rest of those trig functions. The quotient identities are maybe new to you. If you remember on the unit circle, sine's ratio is opposite over hypotenuse, and cosine's ratio is adjacent over hypotenuse. If we divide those two fractions, we get opposite over adjacent, which is our ratio for tangent. And that's why we represent tangent with sine divided by cosine. So we can represent cotangent with cosine over sine. This is all very alien talking like this, but again, we're just talking about ratios. So this becomes this sort of massive puzzle now. With Pythagorean identities, these are the complex ones because they involve squaring trig ratios and functions. So when we look at these Pythagorean identities, they are all describing some sort of Pythagorean relationship. So if we see these when we're dealing with expressions, we might see them as sine squared theta minus 1 equals negative cosine squared theta, for example. We can, in other words, we can rewrite and rearrange these Pythagorean identities so that they're a little bit easier to deal with. And one thing I wanted to point out with these Pythagorean identities, and when it comes to memorizing these things, which hopefully you're comfortable with the reciprocal and the quotient identities already, the Pythagorean ones are a little bit more tricky to memorize. You can start off with only knowing sine squared plus cosine squared equals 1. I get confused with 1 plus tangent squared equals secant squared, and 1 plus cotangent squared equals cosecant squared theta. They're a jumbled mess in my brain. But what I don't forget is that I can start at sine squared theta plus cosine squared theta and take any trig function squared. Well, I can take sine or cosine squared, and I can divide my sine squared plus cosine squared by that trig function squared. So I'm going to take cosine squared theta, and I'm going to use that as what I divide my Pythagorean identity by. And what you hopefully notice is that this is now going to turn into my second identity. So we're going to use this so much that we have really just 3 iterations of the same identity. So we have sine squared divided by cosine squared, that's tangent squared. Cosine squared divided by cosine squared, that's 1, so plus 1. And that equals 1 divided by cosine squared theta is secant squared theta. So you can imagine that if we divided sine squared plus cosine squared, equals 1 by sine squared theta, we would get this last Pythagorean identity. And that's helpful, as we'll see for memorization purposes. It's also really confusing because of how it's written, and I want to point this out. This is sine theta, sine squared theta. I know it looks strange, but it's kind of a mathematician, I guess, shorthand for sine of theta squared. That's squaring the trig function. It doesn't, it's not squaring theta, it's squaring the trig function. So both of these statements are equivalent. I know it's weird, but that's what that is saying. It's a squared trig function. Now we're gonna do these three problems, and I expect to go to the 15-minute mark, so I just want to give you an expectation here. And along the way, I'm going to be talking about my method of why I'm doing what I'm doing, and then some tips and tricks. So for this first one, we're verifying. You might remember proofs. This is very similar. And I know I say that word and people like shudder a little bit, but we are only manipulating one side of our given equation, and we're using the other side as the target so that one side equals the other. So over here, this cosecant theta, that's my target. And I know that because the simplest side of my equation is my target. Let's put that down as the first one. So the simplest side of the equation is my target. The more complex one is the one you want to manipulate. So when we start manipulating this, we can think of a couple things. Are we going to do something with algebra, or are we going to do something with trig identities? So over here, for my tips and tricks, I'm going to put algebra. So we can simplify with algebra, or we can simplify with trig. And you'll see that we'll kind of alternate between those things. So I'm going to kind of explain what I do in my method with algebra or trig. So I can't add together, if I can zoom in a little bit, that's what I'm going to do now. I can't add together sine and cosine theta, cotangent theta. They're not like terms. I'd have to have a sine function plus another sine function in order to add them together. And remember, my target side, this cosecant theta, I'm not touching this side. I just want my left side to equal that side, so I'm only working on this side. So it's almost like simplifying an expression. So because I can't do anything with algebra, I can't add anything, I'm going to do something with trig. And that something is I'm going to turn everything into sine and cosine. Because all these trig functions can be represented as sine and cosine, then this should give me some clarity on what I am to do. And I'll just leave an equal sign here. So that's actually another trick we can do. We can turn everything into sine and cosine. Sine and cosine. Because sine and cosine are, I guess, the simplest ratios we understand. All right, so we did a trig operation to start off with. The next thing we're going to do is we're going to, well, can we do anything more with trig with this? Not really. We could turn cosine over sine back into cotangent, but I don't see any other things from my chart that I can immediately just manipulate into these trig identities. So what I'm going to do is do something with algebra. So my method next is going to be to go to something with algebra. So I'm going to have sine of theta, and you might see the only algebraic thing I can do is multiply my cosines together. And I can't, cosine's not the same as sine, so it's not like my sine goes away. It's still in my denominator, and I still have an equal sign here. So this looks interesting now. It looks like I could do something with algebra. It looks like I'm working towards something with trig as well. I noticed that I've got a trig function squared, and my mind should immediately go to, oh, trig function squared, that's something like a Pythagorean identity. So I'm looking at a cosine squared. It looks like somewhere hidden in this problem now is sine squared plus cosine squared theta. So what I want to do is, well, I can't do anything. I guess I could do something with my Pythagorean identity. So I could straight up replace cosine squared theta. And maybe you want to try this one, but I'm going to do it a different way. And that's kind of the cool thing about these, is you can do so many different methods. You could replace cosine squared theta with 1 minus sine squared theta, with a little substitution. But what I'm actually going to do is something with algebra. So I'm going to do some algebra in my next step, and I'm alternating like rows here. And you should work down on your paper if you have space for it, or if you need to get a new piece of paper. So I'm actually going to do something with algebra for this third step, because I know that if I can just put a denominator on my left side, so if I introduce a sine of theta over a sine of theta to this this sine of theta by itself, that's going to give me a common denominator so that I can add these two fractions together. I can add this fraction with this fraction. So that's what I'm going to do in my next step. So in the numerator of my new fraction on the left side, I'll have a sine squared over sine of theta plus cosine squared theta over sine theta. All right, now this is great because now I see my sine squared plus cosine squared theta. And I'm going to try and shove this up just a little bit so we can all move on here. Oh, I forgot that little guy. Whoops. So my fourth step, it looks like it's going to be something with algebra as well. And that would be combining my two fractions. So I'm going to have a sine squared theta plus cosine squared theta all over sine theta. So now I can see, there we go, another algebra step. Now I can see that, yeah, that is indeed my trig identity, sine squared theta plus cosine squared theta. And I'm going to turn that, I would probably have to start a new line for this, so I'm going to do it over here. But I would have a 1. I would change sine squared plus cosine squared theta into 1, because that's what my identity says, is I can replace one for the other. That's what the equal sign means. So I have a 1, again, reiterating this, my sine squared theta plus cosine squared theta turned into 1 because I used my identity. And my sine theta in my denominator is going to stay there. So now that I know, so this was actually a trig identity that I did, if you're kind of following my methods right here. I used a trig identity to replace sine squared theta plus cosine squared theta, and I'm going to now use one more trig identity to change my 1 over sine theta into cosecant theta. And that's my last thing I need to do, because now I have finally found my target. I've found the cosecant theta. All right, so we've made it through one problem and we're at 15 minutes. Now I'm gonna go on for another 5 minutes with this second example, because I just remembered that I'm the only video for you this week. So I'd like you to make sure you're really absorbing what's going on, because this is it. It is very difficult. I understand, but when we are going to test over this, realize that we're having multiple choice. So what we're going to be asking is, where might there be an error in this work? What would you do here? Sort of questions. Can you simplify these? Can you match these trig functions with, or these expressions with their simplified form, for example? So we're going to look at one more example here before I ask you to do a couple problems, and I'll show you the answers. So for number 2, this one is going to ask us to add these two trig functions, these two trig expressions together. And immediately I see a cosecant and a secant theta. Now my tips and tricks say that I should turn these into sine and cosine. So that's actually what I'm going to do. And I'll still keep my method section here. I'm going to change my cosecant into 1 over sine theta. So I've got this nasty fraction going on. And then over here, my secant is going to be 1 over secant theta. So I've started this problem off with a reciprocal identity. So under my method section, I'm going to put trig. Now, next, I'm going to use algebra to multiply by the reciprocal. Whoa! And you might already see the end to this. Sine squared theta plus cosine. Oh, I didn't actually change that. Plus cosine squared theta. And we can see that our target side of the equation, which I didn't even discuss at the beginning, but it's the simplest side, 1, is our target side of the equation can just be found by using a trig identity, which we already know because we have that chart memorized. So sine squared plus cosine squared theta can be manipulated into 1. Can be just substituted for 1. Great, so that one was pretty simple. Let's try one more. Let's go on. This third one is gonna ask us to take 1 and subtract it from this fraction. Now, I don't like this one because the denominator has addition or subtraction in it, and that looks pretty messy. I'm gonna start this one off. And I'm going to leave the right side alone. But I'm going to start this one off with a trig identity. So my sine squared theta is going to be 1 minus cosine squared theta divided by 1 minus cosine theta. Now, this looks really weird. But I've replaced my sine squared with 1 minus cosine squared theta. So I start off with trig first. And remember, if we go up and look at this little manipulation that I actually did before, I can just subtract sine over to the side of the equation with 1 on it, and now I have a substitution. Or I could subtract, I could do sine squared theta equals 1 minus cosine squared theta. So that's exactly what I did with this one. I've changed sine squared to 1 minus cosine squared theta. And that's going to help me a lot because I'm going to do something with algebra now that is going to have me factor. Do y'all know what 1 minus cosine squared theta is as like a binomial? It's a special binomial. These binomials only happen when you have one term squared minus another term squared. And that's the difference of squares. So because 1 is a squared term and cosine is a squared term, then I get a perfect square factorization. So 1 minus cosine theta and then times 1 plus cosine theta. So this is calling on a lot of your skills for algebra and now trig. And now that we're at this point in the video, I've started this third one and I'd like you to finish. See if you can't find the target there from this point. And I'll show you the answer here at the very end. And I'm also going to start off this matching so that you might be able to see it, and I'll show you the answers. All right, so here's the third verification. All right, so pause the video if you want to work on the matching problems, and then I'll reveal the answer after you've paused, or in like 3 seconds if you just want to see them right now. All right, there you go. Thanks for watching, and I'll see you guys in the next one. Bye.